sklearn, decomposition, sparseencode demystifying sparse representation. The sklearn, decomposition, sparseencode function is a powerful tool in scikit-learn used for finding a sparse representation of a given data sample. In essence, it tries to express each data point as a linear combination of a few selected atoms from a predefined dictionary. This is crucial in various applications where we want to extract meaningful features from data, while keeping the representation as compact and efficient as possible. Here's a detailed breakdown of sparseencode. 1. The core idea: sparse coding. The fundamental concept behind sparseencode is sparse coding. It involves finding a sparse representation of data points using a dictionary of atoms. Let's break down these key terms. Data points: these are your individual data samples, like images, audio signals, or text documents, represented as vectors. Dictionary: this is a collection of predefined atoms, each representing a specific pattern or feature. These atoms can be learned from your data or defined manually. Sparse representation for each data point. The goal is to express it as a linear combination of a minimal number of atoms from the dictionary. This implies that most coefficients in the representation will be zero, hence sparse. 2. The algorithm: lasso regression with a twist. Sparseencode leverages the principles of lasso regression to achieve sparse coding. The lasso least absolute shrinkage and selection operator is a linear model that uses L1 regularization to force some coefficients to become exactly zero. Here's how it works in sparseencode. Optimization problem: the core of sparseencode is solving an optimization problem that aims to find the sparse representation of each data point. Min x, dz22 alpha z1, where x the data matrix with each row representing a data point, d the dictionary matrix with each column representing an atom, z the sparse coefficient matrix, where each row represents the sparse representation of a data point. Alpha, a regularization parameter that controls the sparsity of the solution. Higher alpha values lead to sparser solutions. Lasso's role: the L1 regularization term alpha z1 encourages sparsity by penalizing the absolute sum of the coefficients. This forces some coefficients to be exactly zero, resulting in a sparse representation. 3. Key parameters. Dictionary: this is the dictionary matrix D, which can either be provided by the user or learned using another algorithm, e.g. sklearn, decomposition, dictionary learning. Algorithm determines the method used to solve the optimization problem. Choices include CD coordinate descent, Lass least angle regression, and Lasso's lasso with Lass. Alpha, the regularization parameter that controls sparsity. N non-zero coefs, an alternative way to control sparsity by specifying the maximum number of non-zero coefficients in each sparse representation. Positive if set to true. It ensures that the sparse coefficients are non-negative. Tolerance for the optimization algorithm. 4. Applications. Sparseencode has broad applications in machine learning and signal processing. Feature extraction: extracting meaningful features from data by representing it using a smaller set of basis atoms. Image signal compression: achieving data compression by representing the data with fewer coefficients. Dimensionality reduction: reducing the dimensionality of data while preserving important information. Anomaly detection: identifying unusual data points that are poorly represented by the dictionary. Collaborative filtering: recommending items based on sparse representations of users and items. 5. Example image denoising. Imagine you have a noisy image. By learning a dictionary of image patches representing common features in the image and using sparseencode to represent the noisy patches. You can reconstruct the image by averaging the sparse representations. This can effectively remove noise from the image. 6. Considerations and caveats. Computational cost. Solving the optimization problem in sparseencode can be computationally expensive, especially for large datasets. Dictionary selection. The performance of sparseencode depends heavily on the quality of a dictionary. Choosing a good dictionary is crucial for successful sparse representation. Sparsity trade-off. You need to carefully balance the sparsity of the representation with the quality of the representation. Too much sparsity can lead to information loss. In conclusion, sklearn, decomposition. Sparseencode is a valuable tool for obtaining sparse representations of data. Its ability to capture relevant information with a minimal number of coefficients makes it effective for feature extraction, dimensionality reduction, and various other applications. By understanding the underlying principles of sparse coding and the key parameters involved, you can effectively leverage this function for your own data analysis tasks.